Hi viewers. So last video we have discussed about the electronic transition in UV spectroscopy. So in this video we are going to see absorption and intensity shift in UV visible spectroscopy. So myself, Dr.S.David, working as assistant professor, Department of Chemistry, St.Joseph College of Arts and Science, Cuddalore. There are two concepts there. One was called chromophore absorptions and UV visible spectroscopy. So when come to chromophore concept, it is defined as any isolated covalently bonded group that show a characteristic absorption in UV or visible regions. So some of the examples are nitrile group, carbonyl group, nitrile group, alkene and sulfone group. These group undergo two type of chromophores. So first one is chromophore, in which the group contain pi electron and they undergo pi to pi star transitions. For these pi to transitions, the examples are ethylene and acetylene, etc. The second type of chromophore, which contain both pi electron and n non-bonding electron. Such chromophores undergo two type of transitions. One is pi to pi star and n to pi star. For example, for azo compound, C here means oxygen has this non-bond electron and hydrogen also have non-bond electron. This undergo, azo group undergo n to pi star and pi to pi star transition. Likewise, nitromethane also it undergo two type of transition, pi to pi star and n to pi star transitions. When come to oxochrome, the functional group attached to a chromophore, which modify the ability of the chromophore to absorb light. So when a chromophore are attached with any functional, what will happen? There it will modify the ability of chromophore to absorb light. So altering the wavelength or intensity of the absorption. So otherwise, the functional group with non-bonding electron that does not absorb radiation in near UV region. So with non-bond electron, when you run UV spectroscopy, it does not absorb in near UV region. But when attach this non-bonding electron to a chromophore, what happens? It alters the wavelength and also the intensity of absorptions. It alters the wavelength and also the intensity of the absorption. So oxochrome means a color enhancing group. So last time we discussed that oxochrome do not carry absorption above 200. Common oxochrome group are OH, OR group, NH2, secondary, tertiary and thiol, etc. So I am taking examples of chromophore group benzene. So when you run a benzene in UV spec, it will give a value around 255 nanometer. When we add an oxochromic group, this OH group, what will happen? The absorption getting increases. So I am attaching OH group in the benzene. So phenol, what will get? It will get a value around 270 nanometer lambda max. Same way, when I add amine group, this oxochrome group, to the benzene ring, what happens? It will alter the intensity. That is, the intensity of absorption getting increases for amine to 80 nanometers. So absorption and intensity shift. Here we are going to see four type of shift. One is called as bathochromic shift, ipsochromic shift, hyperchromic shift, hypochromic shift. So bathochromic shift, ipsochromic shift, hyperchromic shift, hypochromic shift. So one by one we are going to discuss. Before entering into the discussions, you have to know the flow chart, wavelength versus absorbance versus wavelength. So here the red shift indicates the bathochromic shift. So whatever the compound moves towards a longer wavelength, we call that as red shift or bathochromic shift. The compound which moves towards a shorter wavelength, we call it as ipsochromic shift or blue shift. The compound which undergo a higher absorbance, we call as hyperchromic shift or hyperchromic effect. The compound which undergo a low absorbance, we call as hyperchromic effect. In the tables descriptively I discussed here. So Bsorption shift or Redshift moves towards a longer wavelength. Hyperchromic shift, Blueshift moves towards a shorter wavelength. So a shorter wavelength. Hyperchromic effect moves towards a higher absorbance. So finally, hyperchromic effect moves towards lower absorbance. First, Bsorption shift or Redshift. When absorption maximum of a compound shift to longer wavelength, it is known as Bsorption shift or Redshift. The absorption maximum of a compound shift to a longer wavelength, it is known as Bsorption shift or Redshift. So what are the compounds that undergo a longer wavelength or Redshift? This effect is due to the presence of an oxychrome or by change of the solvent. So example I am taking here, OH group, Methus group causes absorption of a compound at longer wavelengths. With the example, we are going to see nitrophenol. I am taking para-nitrophenol, shows a redshift. How it shows means when you taken this before adding any alkaline solutions, if you run UV spec, you will get a value around 255 nanometers. When we add this para-nitrophenol in alkaline solutions, if we run the spec, what happened? The absorptions moves towards longer. What value you are getting? 265 nanometers. So what happened here? So when adding alkaline solution, what happens? It removes one proton from para-nitrophenol. So it will become O minus. This O minus, what happened? The negative charge oxygen delocalize more effectively than the unchaperoned. So this O minus undergo delocalization. So it undergo resonance. So we are getting a value towards a longer wavelength. Next, we are going to see Blueshift or hyperchromic shift. So this shift undergo absorption maximum of a compound to shorter wavelength. It is known as hyperchromic shift or Blueshift. So the effect is due to the presence of an group causes removal of conjugations or by change of the solvent. So when you add the group, what happened? It removes the conjugations, or by if you change the solvent, it also undergo moves towards a shorter wavelength. So with the examples we are going to discuss the hyperchromic. I am taking aniline as an example. Our pure anilines shows a Blueshift in us. So when you take aniline, when you run spec, what happens? It will give around 280 nanometer. When we put this aniline in acidic solutions, if you run the spec, what happens? It will give a value around 265 nanometer. So here what you are saying, for aniline, pure anilines, we are getting a peak around 280 nanometer. When you add acidic solution to the anilines, what happens? The absorptions moves towards a shorter 280 to 265, move towards a shorter wavelength. We call this Blueshift. So what happens if you see in the mechanism? So last slide we discussed about removal of conjugations. So the removal of conjugation, what happens? It will move towards the shorter wavelength. So I am taking aniline. So conjugations involving with lone pair electrons. So resonance happening. Okay. If you add acidic solution, what happens? Here there is no lone pair in NH2 group. So lone pair is protoned by acid. So there is no conjugation possible. So the conjugation are stopped. That's why we are getting the aniline salt around 265 nanometer in a shorter wavelength. Next, we are going to see hyperchromic effect. When absorption intensity of a compound is increased, it is known as hyperchromic shift. So I am taking an example, pyridine. So pyridine, if you see, if you run in UV spec, you will get a value 257 nanometer. Whereas we substitute metal position in a second, what will get? Will get a value around 260 nanometer. So here see 257 nanometer to 260. So the absorption intensity getting increases when you add an oxygen group introduced into the pyridine. What happened? The absorption intensity getting increases. Hyperchromic effect. When absorption intensity of a compound is decreased, it is known as hyperchromic shift. When absorption intensity of a compound is decreased, it is known as hyperchromic shift. We are taking naphthalene and 2-methylnaphthalene. So now plain naphthalene shows a value Emax 19,000, whereas when you substitute methyl group in naphthalene, second position, what happened? The Emax value 10,250. So what happened? The absorption intensity getting decreases when you add a group. So 4 types of absorption and intensity are seen. So next we are going to see effect of solvent. So the position and the intensity of an absorption band may shift when the spectrum is recorded in different solvent. Always you have to use a dilute sample solutions is preferred for analysis. Most commonly used solvent is 95% ethanol. It is best solvent as it is cheap, transparent, down to 210 nanometer. Position as well as intensity of absorption maxima get shifted for a particular chromophore by changing the polarity of the solvent. So when come to conjugate, by increasing the polarity of solvent in diene or conjugated hydrocarbon, there is no shift. So when you increase the polarity of solvent, there is no shift in diene and conjugated hydrocarbons. So when you take alpha beta unsaturated carbonyl compound, so alpha beta unsaturated carbonyl compound shows 2 different shifts. One is N to pi star, another one is pi to pi star. Here N to pi star transitions, absorption bands moves to shorter wavelengths, that is Blueshift, by increasing the polarity of the solvent. Absorption band moves to shorter wavelength by increasing the polarity of the solvent. Example, acetone. So if you run acetone in hexane, you will get a value around 279 nanometer, as compared to in water you are getting 264 nanometers. What happened? The absorption band moves towards, so when changing the polarity of the solvent, the acetone value again moves towards a shorter wavelength. Next, pi to pi star transition. Absorption band moves to longer wavelength, redshift, by increasing the polarity of the solvent. The dipole interaction with the solvent molecule lower the energy of excited state more than the ground state. Thank you.